very nice. She didn't want to see any of the angular momentum business. She wanted to see, like, how do you compute volumes of parallelepipeds when I've got coordinates and vectors and the numbers are back in there? You're just going to half fall asleep like the students, aren't you? Okay, I have three vectors. They have coordinates in some canonical basis of 3 space, I, J, K. U, V, and W are the vectors I'm given. I want to know what the volume of the parallelepiped determined by these vectors are. Coincidentally, if I compute this scalar triple product and it's 0, what does that tell me? There was no volume. The volume was 0 is what it just told me. The volume is 0, what does that mean geometrically? All three vectors are coplanar. One of the vectors isn't sticking out and there is no box and therefore there's no volume. So this is a way that Mark also likes to give you questions about. Determine whether these vectors are a basis of 3 space. Any 3 non-coplanar vectors are a basis for 3 space. So as long as their scalar triple product is not 0, then they're non-coplanar. If and only if, right? You're making this, are you comfortable? At least one of us is comfortable. How do I do this? What we know now is the volume of the parallelepiped determined by these 3 vectors is equal to, I know, it's very exciting, isn't it? You're going to watch upside down? Okay. You can do whatever you want when it's COVID. This is going to be U dot product V cross W, the scalar triple product. And then how do we actually compute this? It turns out, I'm going to chew the buttons. Why are you chewing my buttons? Chew the buttons then. The cat tries to nurse me while I'm trying to give videos. What I do is I put the coordinates of U where I, J, K go. So I put U in the first row, 1, and then we put V in the next row, 0, 1, 3. And then I put W in the last row, 0, 1, 2. This is now going to be the volume up to the absolute value. What I need to know now is, though, be careful. I have a 3 by 3 determinant. I can cofactor expand along. I guess for cross product, I always have to use IJK to get it right. But I can cofactor expand along any row or any column. Because I have 2 zeros already, I'm going to choose to do this. So this determinant is equal to -1 times the cofactor C11 and then plus 0, 0. I don't care about the other 2. So this is going to be 1, 3, 1, 2. And this is going to be -1 times 2 minus 3, which is -1 times -1, which is 1. So the volume is actually 1. I don't know what it is. You have to go back to physics, units cubed. Whatever units you were, volume. So this is the efficient way of computing. The moral of the story is, oh, and one last thing I will sneak in there. If you have a pyramid or a prism is 1/6. You can stack 6 of these things inside the parallelepiped. So the volume of a pyramid is 1/6 the volume of the parallelepiped. Syncopated algebra. And then, of course, this is going to be 1/6 U1, U2, U3, V1, V2, V3, W1, W2, W3. So again, the moral of the story is also scalar triple product. You put the first vector where IJK was in either case. If you're going to compute volumes of pyramids or volumes of parallelepipeds using the scale triple product, which is the 3 by 3 determinant. If you're computing areas of parallelograms or areas of triangles, you're computing the norm of a cross product, which will be a 3 by 3 determinant with IJK in the top row. Either way, to compute areas and volumes in 3 space, we're using scalar triple product or 3 by 3 determinants. I'll see you next time. Please subscribe right here and like the kitties.